Lesson 7.7 is on exponential growth and decay. So we've talked about exponential functions. Today we're going to analyze the different functions, and we're going to figure out actually what an equation should be for an exponential function given some information that they're going to tell you. So on 460, if we look at this key concept, the first thing the book's telling us about is exponential growth. So first of all, exponential growth, if you look at the graph, notice how the graph, as we go from left to right, the graph is going up. Y values are increasing, okay? So growth, you think of going up. When you grow, you get taller, okay? Same idea here. This graph, the Y values are going up. So for exponential growth, this is what we're looking at. So the equation for exponential growth, it's going to be y equals a b to the x power. So a few things we need to know, because we are going to be using this. We're going to be substituting numbers in to this equation. So the a is the initial amount, so like the starting amount of something. So that's like when x equals 0. B is the base, and that it's greater than 1. It's called the growth factor. And so the growth factor, how we figure out the growth factor is we take 1 plus the percent rate of change as a decimal. So like, for example, if we had a 5% rate of change, 5% rate of change, you know, as a decimal would be 500. It's 0.05, right? So our growth factor then would be 1 plus 0.05, so it'd be 1 500ths. And basically what we're doing there for the growth factor, just think about if you have the full amount of something, you have 100%. And then if you have a growth of 5%, that's 105%. And then we're changing it to a decimal. That's another way of thinking about it. Okay? So you can either, take and add your rate of change to 100% and then change that to a decimal, or you can say, whatever our rate of change is, change that to a decimal and add it to 1. Okay? Whichever way you want to look at that. So that's going to be the keys when we look for a graph that's got exponential growth. So look at problem 1. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. So if the trend continues, about how much will be spent at restaurants in 2015? Okay, so the variables we're working with, they should use represents instead of equals here, but X represents the number of years since 2005. Y is the annual amount spent at restaurants in billions of dollars. A is the initial amount spent in billions of dollars, and B is the growth factor. So with that information, we can use what they've told us and come up with our equation. So our equation, A is the initial value, so $360 billion. That's the first value that we know, which was 2005. And then the B, if we had 100% and then it's growing by 7%, that's 107%. Move your decimal 2 spots. Or, like I said, 7% as a decimal is 0.07, and just add that to 1 would be 1.07. So this would be our equation that we're going to be working with for this problem. So now we are going to predict the spending in 2015. So what we need to think about is X is the number of years since 2005. So we're trying to find for 2015. So 2015, that's 10 years after 2005. So we need to substitute a 10 in place of the X. So we put a 10 in place of the X. At that point, we could just put that in the calculators. Understand if you were doing it by hand, which wouldn't be a whole lot of fun, you would need to do the exponent first before you multiply by the 360. And then that comes out to about 708. And remember, that's in billions. So about $708 billion will be spent at restaurants in the United States in 2015 if that trend continues. Okay, so that's exponential growth. A lot of people go into the restaurants here. So got it. In 1985, there were 285 cell phone subscribers in a small town. Number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were there in the small town in 1994? And we're going to skip the second part of that. So what we need to think about here is our different variables. So our four variables here, X represents the number of years since 1985. That's probably the most critical one that we make sure we pay attention to. Y represents the number of cell phone subscribers. A represents the initial number of cell phone subscribers, and B represents the growth factor. All right. As you guys do these problems, depending how many problems you're doing, I know that takes a little bit to write all that out. So I'm not going to be too critical on your homework about did you define all four variables every single time. Does that make sense? But understand this one with the X, that's pretty important that you know that's the year since 1985 as you work the problem out. So if we think about our formula here, this is kind of what we're looking at. And then we just need to think about what A and B are. So A is the initial number of cell phone subscribers. So 285 cell phone subscribers we had to start with. When I do the A and then the B, I usually put parentheses just so we can make sure we can see the B is the only thing raised to this exponent here. B is our growth factor. So saying it's increasing by 75% each year. So if you want to, you can say we had 100%. Increasing by 75% is 175%. So if we change that to a decimal, our growth factor would be 1.75, 1 and 75 hundredths. And then the X just comes down. Okay, so the Y and the X, we don't do anything with when we're setting up our equation to start with. Okay, get your equation set first with the Y and the X still there, and then we'll worry about substituting numbers in. Okay, so that's going to be our equation. Now we're trying to figure out how many cell phone subscribers there were in 1994. So from 1985 to 1994, if you subtract, that would be 9 years. And so X is our years since 1985 in this case. So we can just substitute a 9 in place of the X. And once we get to that point, you're just typing that in the calculator. and then see what you come up with. Understand on these, they may not always come out exactly evenly. Obviously, it doesn't make sense to have like 3/4 of a person subscribing, so we'll probably just round that to the nearest whole person. So if we work that out, we're going to round to the nearest whole number is about 43,872 subscribers. So quite a bit of change, and that's usually how technology is, because they start out, those cell phones were going to be, I'm sure they were really expensive when they first came out, and they were probably about as big as the person's head if you've ever seen the initial cell phones that they had. But as time goes on, nobody buys them anymore at that price. It's supply and demand. Then they have to lower the price, and then more people can buy them. Or it catches on, and more people are interested in it maybe too. So here's a problem that's not in your book, just to get a little more practice with this. Suppose the population of deer in a region was 3,500 in the year 2000. And since then, population has grown by 3.5% annually. And the question is, they want us to figure out what the population is going to be in the year 2020. So we're going to start out with our formula here. Again, I'm not going to get real technical about laying down all of our variables. We're just going to think about what we've done. If you want to think about for sure the x and what that is. The x is always related to where did we start at with the information they're giving us. So in this case, the year 2000, that's our starting point. X is going to be the years since 2000, okay? And I know that's kind of not real, I'm not doing let X represent the number of years since 2000, but you get the idea. So based off of that, our initial value was 3,500. Our growth factor, if you can think about 100%, and it's growing by 3.5%, that's 103.5%. So that'd be 1.035. So this is our equation first of all, okay? Don't rush yourselves when you do these problems. Get the equation first, and then we'll substitute. So 2020 is 20 years since the year 2000, so we'll put a 20 in place of X. And then we're ready to work that out. And again, we're talking about how many deer there are, so we'll round this off to the nearest whole number again. So that would be about 6,964 deer in the year 2020. Okay, now obviously there's a lot of different variables that go into this. Lots of things, reasons why, that was in 2000. By the year 2005, the year 2010, this growth might be looking totally different, okay? I've read about different diseases and things with deer. I mean, there's lots of different variables and things that'll affect that population where, 20 years from now might be a totally different story. But this is what we're predicting based off of what they're telling us.